Okay, hello from the Rubenate Sleep Science Center. My name is Valerie. I just wanted to welcome your classroom to our museum. We focus typically on sciences such as physics, astrology, and chemistry. So today we have Gomer and Grace to show you some exhibits, so please enjoy.
I will.
Hi everyone, my name is Gomer. Thank you for the intro. So I'm a fourth-year aerospace engineering student at UCSD, and today we're gonna talk a little about magnets and electromagnets. We hear that you guys are learning about that in your physics. So what we have here is magnetic pendulum, and the way this works, we have a copper coil here, and we have magnets here. And then this is connected to this gauge right here that shows you how much current or voltage you're creating. And then this is connected all the way up here to this one. And we also have a switch here. So the way this works, if I have the switch in the center, the switch is open. So that means these two are not connected together. So if I move this one, nothing's going to happen. But if I bring this here, because of conservation of energy, the energy that's created here, it's passed on to the other one, and they move in phase because these two are connected in phase. The polarities are correct. But if I flip it the other way, these two are switched. So the wires here are flipped. And so if I move this back and forth, the other one should move the opposite direction. And this is happening because of conservation of energy.
Hey, can you do that again, but get the camera closer?
Sure. So,
Thanks.
So I'm moving this one, and the other one moves on its own. If you want to get the other one.
So what he did was he reversed the phase. If one goes back, the other one moves forward.
Yeah. So so now the phase is changed. Now they should move together. The other one's not as much. I don't know if it's the conductivity, but there we go.
Yeah, the switch has to be all the way over, connecting it.
Yeah. So
that gauge that's in the middle of the two, what's that showing again?
it's showing how much voltage you're producing. So if there was a light bulb, it would turn on.
Okay. Ooh.
What's the amp?
Actually, that's current.
Current, yes, sorry. The current. There it is. There we go.
So, Gomer, the voice you're hearing, this is Mr. Termath. I know you've been working with Roger, doing like the sound checks, in the previous days.
Okay.
Just real quick, you said you're a fourth-year aerospace engineering, yes?
Yes.
Okay. When I went to Cal Poly San Luis Obispo, I used to be an aerospace engineering major. So I completely understand everything that you were going through right now in your course of study. So, I mean, I speak the same language as you, except it looks like you're going to graduate with a degree in that. I did something else.
Okay, right on.
Okay.
Awesome.
Just thought I'd throw that in.
Sorry, what was that?
I just thought I would throw that in.
Oh, okay, awesome. So you're one of us. Grace is actually, I'm going to hand it over to Grace, and we're going to show you the next exhibit. But she is also, I'll let her introduce herself and tell you a little about herself.
Okay, thanks.
We're going to move over to the next one.
Hi everyone, I'm Grace. Can you guys hear me?
Yes. Can you hear us?
Okay. Yeah. Alright. My name is Grace Zhang, and I'm a third-year aerospace engineering in UC San Diego. And then right here, this is how usual generator looks like. So here is copper wire, and then there's several loops of it. And then right here is magnetic. So there are two magnetics on here. And what I'm gonna do is I'm gonna put energy by moving this acrylic plate, and there's a light bulb here. since energy is conserved, and then I'm putting energy into the system will like light the light bulb. And then, so while I'm moving this wire and then makes magnetic field to make electrons out of the system, and it will like light the light bulb. I know it's really like hard to see the light bulb light up because it's really like I'm going by really fast. But I hear you guys have this sample at your classroom. Is it right?
Generally, yeah. Can you get the camera as close as you can to that light bulb? We knew when you guys did a test yesterday or last week, the light bulb it's not really showing up too well on the video. It's like while it's not moving, can you get the camera like really close to where the light bulb is?
Yeah, sure.
Okay.
Can you move the camera really close to the light bulb? And then like move the camera to like 90 degrees. Alright. We'll do that right now.
So
light bulb is right here.
Yep.
And then
Wow.
can you guys see the light bulb lights up?
Yeah. You see it as a streak. It's on the very top, like above that white handle. So there's the bulb. Okay. Now it just very faintly lights up. You know, when you're actually in the exhibit, yes, you're seeing it.
Mr. Chairman, he'll show you later, right?
Okay, yeah.
You might remind him.
So you can see the filament. It's just this bright dot. It turns on and off very quickly. Like as soon as she stops moving it, that bulb goes off. Okay. So it's just this little orange spot when it lights up. It only lights up when it's moving, which naturally makes it harder on video to see it. But yeah, do it like 2 or 3 more times, just like you did it.
Sorry, what was the time?
I say like you push it like in and out, 2 or 3 more times.
Oh yeah. Alright.
Okay, so now do you see it?
Mr. Chairman, can you ask for instances on that?
Okay, Grace, I had a question from a student. As you are, pushing this, what is basically a lot of coils of copper wire, as you're pushing it again in and then pulling it back out, is it giving like any resistance? Like, do you have to push harder on it?
Sorry, pardon me.
Yep. Like, is it fairly easy to work that apparatus, or are you experiencing like, is there like any force of like resistance on that thing?
So you're asking me if there's a resistance in this system?
Yeah, like is it easy to work that, or do you have to like?
Is it hard to pull it or?
Yeah. Okay. So do you have to like exert a lot of force on that?
Oh, actually, you don't have to, because it's but if you put more force on, then the light bulb's gonna light up like brighter. But with like a little bit of force, it will still light up because it's magnetic and the copper coil that's making like the light bulb light up.
Okay. How many times does it look like that copper wire is looped around? Like, it's definitely a coil of it. Like, how many like individual strands do you see? Like, rough estimate.
There's like so many. Do you think you can zoom up on the wire, please? There's like a lot of loops, as you can see here.
So the loops are actually like layered, almost in a stack. Okay. Yeah. So guys, you did this yesterday with your, as I told you to make more and more loops with the wire and hooked up to a battery. Okay. Now pretend you did that many, with your experiment.
What?
So it's going across, plus it's layered vertically. So there's probably at least 50 or 60 loops. Easy. Okay. Grace, I'm going to do a quick little demonstration using another little apparatus I have here in the classroom. Can you guys just hang on for about a minute, 2 minutes before moving on to the next one?
Mm-hmm. We'll do that. So I'll call you in a minute.
Okay. Thank you, Grace.
All right. Bye.
Hey.
There we are.
Hi, everyone. Welcome back. So we have another exhibit here. This is a DC motor. And Kim, if you want to come around real quick. So the setup here, we have it's similar to the other one. So there's a coil inside with magnets around it. And here's an external magnet over here.
Wow.
And then here's a switch. So the switch is off right now. What I'm going to do is turn this on. So this coil now has current going through it. So this coil is all current running around it. And as you can see, this is not moving or anything. But if I take this magnet close to it, then this thing starts moving. It's spinning pretty fast. I don't know if you guys are able to see it or hear it. Maybe you can hear it when I get closer. You guys hear it?
Yeah. Can you put the camera instead of looking down on it,
To the side?
Yeah, from the side, so that we can look into that tube.
Yeah, so if you want to get looking into the tube, go a little bit lower.
What? Picture's not quite as clear. Just let it go.
Okay.
We see it, but it's
So what I'm going to do is take this off, and maybe you guys can see it slow down and stop. Just to use a reference, there's a screw on here. Maybe you can see it stop.
Yeah, on this reestablished connection, the picture quality is not quite as good as what you guys started with.
Oh, okay. Yeah, we went upstairs and came back down because we didn't have a connection up there. So we just reconnected down here.
Okay.
Yeah. Saying the quality is not as good as before, the last time.
Okay. Yeah, if you lower the camera, so it's looking at that object from the side instead of from above, it gives us a little bit better view.
Okay. We can get it from the side, from here, looking onto it. How is that? Is that better?
Oh, go around.
Oh, to this side?
Yeah, so we can look into the tube. Yeah, there we go.
Okay, cool. Now what I'm going to do is, so the switch is on, now I'm going to bring this magnet closer. Do you guys see it spinning right there?
Yeah.
Oh, yeah.
Yep. So it was previously not moving before, but moving the magnet next to it gets it going?
Yeah.
Okay.
Yeah, so back here it's not moving at all. It just stops. And then if I take this magnet closer, so we can do an experiment, see where it starts moving. So there it starts moving a little bit. And it's not as fast, but if I move it closer, it spins faster and faster. And the application with this could be wind turbines. They kind of work in a similar way, except this will be a generator. And so you would have a propeller spinning out here and generate electricity. So this would be reversed in a way.
Wire spinning, and then they move the magnetic field to it.
Yes.
Oh, they're behind you.
Okay.
Yes.
And then over here we have similar ones and exactly reversed. So if we spin these, then the light bulb turns on over there.
Will the light bulb brightness be affected by how fast you spin?
Yes, it is actually. So Grace, so these two are actually connected to the same light bulb. So Grace is going to help me spin the second one, and then I'm going to spin the first one. So ready? We're going to start slow, and then if we move faster, the light bulb gets brighter and brighter.
What are those gauges behind the motor?
So these are actually this is showing the amps that we're generating. So okay, so I'm going to spin this one. And I'm getting about half an amp when I'm moving mine. This is kind of slow. Let me see if I can get it faster. So yeah, about half an amp that I'm producing with this one. but these two are connected together, and here's a switch. So light bulb turns on. If I turn the switch off, it shouldn't turn on at all.
How many amps can you get when you spin that as fast as you can with one motor?
With one motor? Okay, let's see. I'm getting about, I would say about 0.8.
0.8?
Yeah, 0.8 amps, close to 1.
Huh. So you're putting in like all of this work input, but you're only getting 1 amp?
Yes.
That's interesting.
Oh, cool. Well, the other one's also spinning.
Right.
Yep. Oh, another student just said it sounds like, or looks like the other motor starts spinning as a result of the first one.
Well, that's right, because they're connected together, so the other one starts spinning as well.
It's like a tandem bicycle. Spin both ones.
And I think that's another reason why we're getting less amps here, because this one's drawing some of the amps that we're producing to move the other one. And this is because of conservation of energy. So here, let's try this. I'm going to open the switch. So technically, I don't think this should move the other one, or it actually moves it more now. The light bulb's out of the question now. So look at the difference now. With this, I am moving this and turning the light bulb on. And here, we're only producing, do is take this light bulb out. So I'm going to open the switch. You can see these are spinning at the same speed.
That's crazy.
See that?
Nice.
Yeah, I saw it.
Okay, so all that work input that you're doing, I was hoping you would mention energy of conservation, because I mean that's exactly what it is.
Yeah. So yeah, the energy is conserved. It's getting transferred from this one to this one because of the connections and because energy is conserved. And also by generating this, the light bulb also turns on because of that energy is transferred from here to the light bulb, and that's also conservation of energy.
Okay, so you're getting a mechanical energy input as far as spinning that first motor, and you're getting, like when that switch is closed, you're getting output of light energy and mechanical energy.
That's right.
But, you know, naturally if we took that second motor out, the light bulb would probably light up more.
Yeah.
Just like when you take the light bulb out of the circuit, that motor, second one, spins practically just as fast at the same rate as your first one.
That's right. Exactly.
So,
and here, we also have the voltage as well. This meter shows the volts that we're generating.
Okay.
So this is about 10 volts that I'm generating with me spinning this thing pretty fast. See if I can get this down to 20. 15 is the most I'm able to get when I spin it as fast as I can.
How many?
asked you a question.
Okay, sorry, say that again.
So I tried spinning as fast as I can to see how much voltage I was able to produce. So with normal speed, I'm about to, I produce about 10 volts. And when I go as fast as I can, the highest I can get is about 15 volts.
Okay. So really, it seems like like your best peak voltage is 10 volts, and you have to expend all of this work just to get an additional 5.
Exactly. Yeah. So the first 10 is easy to get, but the rest you need more work.
Okay.
Sweet. Any questions? I'm having all the fun, but what about you guys?
Right there.
Oops.
How much is the charge?
The charge?
Yeah. His voltage is whatever of the coulombs.
Okay. Do you want me to try to answer, or do you want him?
Him.
Okay.
It doesn't matter. I want like 20 minutes.
Okay, so you want the number of coulombs?
Yeah.
Okay. Okay, I have a student question, Gomer.
Yeah.
He was asking, with 10 volts, if that's what that's the voltage difference you're producing, how many coulombs? Like, what's the charge if you have 10 volts?
What's the charge? Okay, so so right now I don't know this off the top of my head of charge of an electron, but I would. So you would just divide, and you could figure out how many coulombs would take for that many voltage.
Okay.
Sorry, I didn't.
No, I know I could almost answer this question for you as far as something you could say to kind of, cover your end. If you're an aerospace engineering major, our expertise is in making that thing fly.
Yeah.
Not necessarily how much current or whatever's going through it off the top of our heads. So, I mean, that would have been my answer before I got out a book or some notes to refer to.
Yeah. So I wasn't able to answer that question off the top of my head, but
there's an equation that we can dig back up. We've done it. If you know how many, so I think, let's see.
You have a buttload of voltage. Don't look.
So we have it's electric potential. Remember? Now electric potential energy, or excuse me, electric potential is the electric potential energy per charge. So we know the electric potential. That's the number of volts. So we would have to work with that kind of an equation. So that was chapter 34 or 33. Okay. All right, so we're getting that question addressed, but we're ready for any next.
So we're gonna move on to our next one. We're just gonna walk over to the next pendulum. Thank you for addressing that question. Yeah, like your teacher mentioned, we're aerospace engineers, so we don't deal with most of the electronics, but it is always good to have a good background in all this stuff.
Yeah, because granted, aerospace engineering does incorporate electrical engineering. You have to know about controls.
Exactly, yeah. So, kind of crowded here, but our next one is this pendulum here.
Okay.
So, again, we have magnets. So these are all magnets down here. And then, so this is where the conservation kind of comes in as well again. So if I move one of these, I kind of start moving all the other ones just by moving the first one. This is because that energy is transferred through all the way. Pretty cool.
My students are saying, and I quote, "That's so cool."
Yeah, it is pretty cool. Check it out. Now I'm gonna stop this. I'm gonna move the middle one only. Let's see what kind of pattern we get this time.
Okay. So he wants to move just the middle one to see what happens.
It's like birds are flying.
Pretty cool, huh?
How many of the two M ones?
There it is.
Oh, I had a request. Student wants you to move on opposite ends.
Okay.
Move both outer ones. So the ones that are on opposite ends.
Okay. Great. If you can help me move the other one. Do you want to move in the same direction at the same time?
Do actually 2 rounds. First one, do same direction, same time, and then do opposite directions.
Yeah. So we're gonna go this way first, and then. Okay, ready? We're gonna go in the same direction first. Ready? Go.
Oh wow! No, same direction. Whoa!
Okay, so they're trying to match up their. Okay.
It's still happening. Make something happen.
Okay.
Broke it.
Okay. Now I'm gonna slow down. Grace, continue that. I'm gonna slow down and go in the opposite direction. There you go. Not much difference, huh?
So as a whole, they're kind of moving, but not nearly as much if you did one, just one only.
Yeah. So there we go.
That one is moving. Look at that.
Yeah. But it looks like the motion is being caused by the one that Gomer has, and Grace's one is completely out of sequence or something.
Yeah. So okay, Grace. Let's try to keep it in sequence. So let's move together. Okay. Try to match mine.
Oh wait, there it goes. So I think smaller amplitude gets it going.
There you go.
There we go.
Yep. Yeah.
Third one's like trying to.
So actually, here's an interesting question for both of you, since you're engineers. Is there any possible real-world applications that you would know of that uses this kind of an apparatus to make it work?
That uses this kind of apparatus. Great. Can you think of anything real world that would use this kind of apparatus? Like in a aerospace?
This is called a challenge
Aerospace thing?
on the fly.
I don't know. I'm trying to think what we could do with magnets.
Tell them to spin it all the way around.
Trains? I don't know.
I think that
Yeah. High-speed trains, maybe?
Woo!
The high-speed train?
Yeah.
I know, thank you. I said it.
Very likely. It sounds like or not sounds like. It looks like those magnets. They're like all attracting each other.
Okay. Yeah.
And I
They
know,
are. Yeah.
I know, like on a high-speed train, you wouldn't want necessarily magnets to be attracting each other.
So you would flip them.
Yeah, like, or at least not all at the same time. Because you need something to get it going on the track, but you know, it's not like, say, like a regular train where it's in contact with the track. It's got to be, you know, the magnetic field, you know, has to be doing, you know, keeping that train off the ground.
Yeah. And now we need to reduce the resistance or the drag or the friction caused by the train tracks.
Yep.
That way you can go faster and use less energy to get across, I guess.
Okay.
So I think we're going to wrap up now. This was our last exhibit we wanted to show you guys, and here you guys are almost. So,
okay.
From the Science Center, do you guys have any more questions? Sorry, I'm kind of.
Yeah. Any questions about what we've seen? Any questions for them, knowing that they used to be high school students, now they're in college?
Yeah.
They used to be. Any questions about UCSD?
Yeah, any questions about UCSD, engineering? And I don't know, I was personally high school. I know it seems like a long time ago, but all the physics and math classes, those are the fun ones, in my opinion. So, continue those and keep your grades up and go to college and become aerospace engineers.
Nice. Actually, where did both of you go to high school?
What's that?
Where did both of you go to high school?
So I went to Verdugo Hills High School. It's up in LA area. Grace, where'd you go to high school? Corona High School.
Ramona. Nice.
Corona.
Corona.
Corona in Riverside.
Okay, yes.
Yeah, so.
Did both of you get enrolled at UCSD? Like, did you come like straight out of high school and came in as freshmen?
Yeah, so we both came in as freshmen, but another route to take would be to go to community college and then transfer. But when you're here for 4 years, you get to work on a lot more projects and get to know professors that they're doing cool research. I would think that's one of the benefits of going to a 4-year program straight out, because of just all the different programs that they have and all the professors that you can make connections with and learn from them.
Nice.
All right.
Ooh.
So,
there's 5 questions coming in at once. One question I just got asked is typically, like, what SAT scores do you have to get into UCSD?
SAT scores. Average, what's the SAT score average now? It's like up in the 1800s? I don't know. But I personally, my SAT scores weren't so great. I had what, like a 1800 or 1500? I can't even remember now. My SAT scores, I would say, it really depends. When you apply to college, it's not just your SAT score, it's not just your GPA. I would think they look at everything. So they do look at your scores, they look at your GPA, but they also look at what you kind of do on the side as well. So if you guys have any projects you work on, you could write that in your application if you're working part-time somewhere. So I would think, yeah, we're volunteering. So I would say study hard for the SATs, but don't worry so much about it, but also get involved and try to be well balanced. And that helps a lot. But typical SAT scores would be anywhere from like 1,500 to and up in the 24. So it's broad. We have the best of the best, and we have some of the students who are on the lower end, but we're still here and studying and keeping up with all the other guys. So
nice.
Yeah.
Great answer. Thank you.
Awesome. All right. Well, thank you guys, and hope you guys have a great rest of the week. And don't forget to do your surveys as well.
Thank you. They're working on them right now.
Awesome. Perfect. Thank you guys.
All right. Thanks.
All right. Bye-bye.